Let's look at polar coordinates. This is another way of how we can use trigonometry. Okay, so let me start out with a point here. Let's say, now I'm drawing that in a pretty upscale way over here, but a point that we usually know, right, on a point here. Say a point at 1, 1, for example. So the first number in a pair right here is the x value, right? The x coordinates, and the second number in a pair right here is the y coordinates. And so together we got any one of our points here got coordinates with the x and y values, right? So this way right here, at this point we call that the style, how we indicate the coordinates of a point is called rectangular coordinates. You guys see the picture here is anywhere you got, you put your points, right? Then you draw the x coordinates right here and the y coordinates right there, so together you come up with a rectangle from the origin. And the origin is of course 0, 0. See what I mean? So that's why it makes sense to have that name like that. So the way how we usually know about coordinates, we call it rectangular coordinates. Now a little more specifically, rectangular coordinates is also known as the Cartesian coordinates. Right? So from now on, when you hear Cartesian coordinates, it's the same as the rectangular coordinate, where each point that you put on the plane has values, has x values and y values, and when you trace out those coordinates values, right, they form a rectangular shape again. That's why it's called rectangular coordinates. But like say, additionally, we can call that the Cartesian coordinates. And so the point is still the point. The point is still the point. But now I'm going to redraw the exact same picture, but I'm going to put in some further explanation right here. Still the same point as a vertical axis, as a horizontal axis. We can name that x and y, right? Let's put the point right here again at 1, 1. That same point like that, right? Now think about it. It's just the nature of it, and at this point you guys have already learned a lot about trigonometry. So at this point here, any point makes some distance to the origin. See what I'm saying now? Any point that we put on the point, a point here, a point here, a point here, any point makes a distance where we call it the radius. Right? So that distance right here from the point to the origin, we call that as the radius. That's formally radius. Distance from the point to the origin. The origin as one point itself, we refer to that as the pole. So right here at the origin, we call it as the pole. It's the same axes, it's the same vertical and horizontal axes right here, the same set of axes. Right? And they've got having the same origin, and put a point there. So from where the point is referenced back to the origin, right? There is a distance. We call that distance the radius. So how much distance that is. See what I mean? Right? And then the origin itself, we used to call it the origin coordinate at 0, 0, but now in the new language we call it the pole. Right? The origin of our set of axes is right here, we call it the pole. You guys agree on that still? And then from where the point is, any point that we put on the point right here, it's always going to make some angle away from the positive x-axis. So we take the reference to the positive x-axis right here. So any point here, right, makes some angle with the positive x-axis. See what I mean? Call it angle theta. Right? And so angle from positive x-axis. That's the angle theta. This one here is the radius. So the radius here got lowercase and capital K, it's all your choice, the letter R and the radius. Sounds good? And so now think about it. Can you calculate how much angle there is? We already knew that the point here, that point in rectangular coordinates, got coordinates 1, 1, 1 for x, 1 for y. Okay, and I made a lot of explanation there, but now in that way, how much angle is that from the, as a positive angle over here, how much angle is that from the positive x-axis? take out the picture right here, right? Right? The pole is right here, 0, comma 0. And 1, comma 1 is right here. How much distance is that, and how much angle is this? We can find that out. So we've learned from trigonometry. We've learned from trigonometry way earlier in our much earlier lecture here. Any points making a distance with the origin. So that distance right there is done by what? The radius is square root of x squared plus y squared. You guys remember that? The square root of the x coordinate, the square root of x squared plus y squared, where x and y are your coordinates of the point, right? So we've learned that formula from earlier. So for a point like this, the radius here in this problem here specifically, I'm demonstrating the idea. Square root of, see, 1 squared for x squared, right? Plus 1 squared for y squared. So it's going to be, it turns out, the radius square root of 2. See that point right here, sitting at radius square root of 2, that distance. And we got the radius. So how much angle is that? I mean, you can easily estimate, the idea we can easily estimate with trigonometry. Or we can estimate, even with basic high school geometry, you can tell the triangle you have here is 1, 1, and square root of 2. Right? What kind of triangle is this? It's a right angle right there. From just basic geometry, we don't even need trigonometry here. From basic geometry, this triangle is a right isosceles triangle. Right? That's these two sides are equal. And so isosceles triangle means these two angles have to be equal, right? Have to be the same measurement. It's 90 here, and these two unknown guys are equal. So it has to be 45 and 45 here, right? So the angle theta we're looking at now is angle theta is 45 degrees. That's what is an easy one. So after doing some of those demonstrations right here, my point is that the same point we put here, right, with the other laser that we're looking at, it makes some distance. It makes a different distance square root of 2 from that pole. And it makes an angle, a positive angle from the positive x-axis being 45 degrees. And by the way, 45 degrees in your trigonometry understanding is a pi over 4 angle, right? And so here's how I'm seeing it. Let me erase this information here. So this same point, 1, 1, right, is or can be expressed. Same point can be expressed as. So we've got radius 2, angle pi over 4. The radius, comma, angle. Radius and theta. Or you can also express that in degrees. Radius 2 from the pole, right, and being at 45 degrees positive degree. See what I mean? And so that same point can be expressed in terms of radius and how much angle it's opened up. So we refer to this style, we refer to this convention of expressing the point here. It's a new style of expressing a point here. We call this is polar. What we do here is polar coordinates. We're indicating the position of the point using how much radius it makes from the pole and how much angle it opens away from the positive x-axis. You know what I mean? So 1, 1 is the same point with 2 for radius, and angle pi over 4 for radius 2, angle 45 degrees. Right? And then that's not the only way of how we're expressing it. Now, right now I've been saying with the positive angle, but when you've learned enough trigonometry, angles, positive angle or negative angle, it all depends on how you want to perceive. Now, from the x-axis here, right, you can also go clockwise, you can see what I mean? So, as a negative angle, to reflect a clockwise rotation right here, then the same point, again, radius 2. But how much angle is that? Negative 3 300 and what? 15 degrees, right? I'm saying that. You can also think of that as a negative rotation right there, that same angle. Same point, radius 2, right? Being a negative angle. Or radius 2, in radians for our angle minus 7 pi over 4. All the same point. So these points are all different ways of how we represent the same point here, the polar coordinates. Right? That's the beginning idea of what polar coordinates is all about. Okay. All right, so now at the bottom line right here, a little more generally, x and y coordinates, right? We pick a point, any point sitting at x comma y. So there's an angle theta there, right? And then there's a radius r. So we can write r comma theta. Okay. X comma y can be expressed as r comma theta. This is the polar coordinates. And then this is old style over here is rectangular or Cartesian. Cartesian coordinates. And then from what we drew out from that demonstration problem right there, then the radius, now if we go from Cartesians, if we already knew the Cartesian right there, then the radius is simply just the square root of x squared plus y squared. That's how we get the radius. If we go from the Cartesians over to polar coordinates. Then a little more specifically right there, then the angle theta, it all depends on how we want it. So angle theta can be done by, you can go sine inverse, right, of your y value over the radius, or you can go with theta equals to, you can go with cosine inverse, your x coordinates over the radius r. Or you can go with even more directly. Theta can be done by taking the tangent inverse of y over x. We don't have to do all three, it's just one route is good enough. I mean, the earlier picture when it was plotting it out, I didn't even get into any of the trick, the inverse trig function, because it was easy enough for us to see right here. But if we were doing that a little more properly right here, then at the point 1 comma 1, right? 1 comma 1 is here. Right? The pole is here. This is x value, this is y value. Right? That's what the 1 comma 1 is all about. And so to calculate your angle theta, right, as a positive angle, you can go sine inverse, take the sine inverse of the x, the y value being 1 divided by square root of 2. You guys follow it? And that will come out, and 1 over square root of 2 is the same as square root of 2 over 2. Same as sine inverse of square root of 2 over 2. So that, needless to say, it comes out here pi over 4 angle, right? Or the 45 degrees angle. That's how I got this value. So the sine inverse is a lot of times that we learn from our convention about the sine inverse. The sine inverse only come out with angle in the first quadrant, or anywhere from minus pi over 2 to pi over 2, right? So that's something you got to be aware about. If you run your sine inverse function like that, then the angle that we are expressing got to be an angle that stays anywhere from minus pi over 2 to pi over 2. So this angle right here, we call it pi over 4. And then you can also use a cosine inverse. So my point again is, when you try to get the angle of the angle at the center right here of your coordinate point there, right? Then you can either go with sine inverse or cosine inverse. So if you decide to go cosine inverse, that's x over r. So r, the radius, is famously the square root of x squared plus y squared. Okay? And then the angle over here, you've got one of these three choices to go with. Right? So when we're actually doing polar coordinates, no, radius, as far as an actual value over here, radius has to be positive, right? Because it's the actual distance from where the point is to the pole over here. But now, when you're reading a polar coordinates representation, sometimes you may see people writing like this, a minus radius and some angle theta. So what's up with having a minus radius? See what I mean? Like say, people tell you, hey, plot the point, right? Let's plot the point minus 2 and then 45 degrees, for example. It's a point in polar coordinates. So here's how it does. Here's how it's done right here. Here's how we can do it. The way how we do it, we search for that 45 degrees line right here. See what I mean? So 45 degrees line, that's the positive angle, even though it's written after the radius in a pair right here. But we search for the angle first. We search for the angle. But then instead of positive 2 coming out this way, right? We can still go positive 2, but then we take the opposite side right here. See what I mean? That's the way how we handle a point with some angle and having negative representation of your radius. Okay? So 45 degrees, right? But instead of taking the usual radius 2, we're going to take the opposite one right here. So it's going to be on that same line, but it's sink down this way. So this point right here is minus 2, comma 45 degrees. Okay? So let's get comfortable with plotting. So let's call that example 1 here, so that we can get comfortable with plotting the polar coordinates point here. So I'm going to go in a mix between degrees and radians and all that. Now when we're doing a plot, right? The point that we have on the board written in the example 3, 30 degrees. So the way we plot, and you have seen that a little bit in my demonstration before we got into the example, we search for the angle first. And right now the angle is a positive angle, right? And we always go from the positive x-axis. 12 angle right there, which is a 50 degrees, right? And then the pi over 6 is right up here, right at that grid right there. You guys see that there? Right? So that's the equivalent to your 30 degrees. Sound good? Right? So from the positive x-axis, the axis is still the same, exactly the same, just like how we've been knowing it. Right? So now from the positive x-axis, I'm going to make a positive rotation because the angle was reading, radius 3 and angle 30, right? So we're going to make a positive 30-degree rotation first. See what I'm saying? So it lands right on this line, right? This terminal side of the angle right there. See what I'm saying? Right? So 30 degrees right there. Right? So right there with 30 degrees, about right there. So now we're going to look for radius 3. So these concentric circles are indicating the amount of radius being away from the origin. So now on that line being the pi over 6, 30 degrees, radius 3 is about right there where I put my mouse cursor. Of course, I'm a little bit off scale right there, right? But that's where we put it. So now you guys go ahead and locate that the same on your paper as well. So we locate once again, we do a rotation. Think about creating a positive rotation as required by the prop, right? And then from there we land, right? When we land into that line right there, we're going to start looking for radius 3. So radius 3 on my scale is right about right here. Right? And that's so precisely 30 degrees, right? Now it's all completely in degrees again. So that's the point that we're putting it down, right? You know what I mean? So once again, I search for a 30 degrees angle. And then right when we're on that line right there, when we have landed on that line right there, we're going to search for radius 3. So the radius 3 is, so we're going to just, from there, right on that positive side. Like so let's try another one. So how about 2 minus 3 pi over 4. So now the point here in radians, here's how I'm seeing it. The angle, right from the beginning, the angle was indicating negative. So, and remember now the routine that we're doing here, we search for the angle first. We go with the angle rotation first. So the angle rotation was indicated negative, right? So I'm going to search for it on my graph right here, on my graph grid. Right? I'll go, this is a pi over 4 right here, the negative pi over 4. Negative pi over 4, that's right. Negative 2 pi over 4, negative 3 pi over 4 is I'm right about there. See what I mean? Right? Minus 3 pi over 4 is right here. Right? So now I'm going to put in pi over 4. Now radius is 2. Length of point right there. You guys with me on that still? We can rotating from 0 to the positive x-axis, right? Pi over negative pi over 4, negative 2 pi over 4, and negative 3 pi over 4. We land right on that angle, and we land at that radius being that distance away. So remember, we search for the angle first, and then we're going to start looking for the radius, depending on how it goes. See what I mean? So let's try another one. So first, I'm gonna the angle. The point was instructed to be minus 2 for the radius, but 75 degrees angle. So we're gonna search for the angle first, and the angle right now is indicated as a positive angle, right? So we just search for that angle right there, and then the rule when we're running into a negative expression of the radius, we're gonna take the opposite side of that. Right? So now on my picture right here. Right. So 75 degrees. 60 is here, another 15 degrees are about right there on that line. You guys see that there? Right, that's where I put my mouse cursor. Right? But now we want radius minus 2. So radius 2 is about right on this concentric circle where I put my mouse cursor at. But that's not the right point, right? This is positive radius. Because that's the angle 75 degrees right there. When we turn up, you got the point test, right? But now negative, we're going to have to take the opposite side, so the right point to land is down here where I put my mouse cursor at. You guys see that? Okay. All right. And so let's see. You go ahead, put the point right there, and then we're going to double check that with the decimal over here. So the angle is 75 degrees and minus 2. See that? What happened? Both values are negative. So we go minus 1.5, right? And then minus 60 degrees. All right, so on my picture again, remember the rule is we search for the angle first. So the angle this time is indicated as a negative angle, right? The angle was indicated as a negative angle, negative 60. So I'm going to go down 60 degrees right about here, right where my mouse cursor is pointing at. You guys read that on that line here, where my mouse cursor is at. That's negative 60. And so the concentric circle for 1.5 radius is not too clear. It's not labeled. So the radius 2 is right here. You guys see how I'm putting my mouse cursor on that circle? But then 1.5 is about this circle right here. Okay? So once again, negative 60 and radius, but this is radius 1.5, so radius negative 1.5, we're going to take the opposite side right here, so it's lands about right there. See what I'm saying now? That point where we're putting it. All right? And so, now with that, I'm going to put it in negative 60, right? And then negative 1.5. See how it's consistent with what we were predicting with that? Now let me put in these problems for you guys to try on your own. Okay, so let me show it on the screen right here. You can compare it. So first point that I put on that list is that radius. I mean the angle is 105. So we search the angle 105 degrees, and we're at radius 1. Does that look like the point that you drew right there? That point in red that just now popped out. Okay. So the next point, the angle is 330. And I'm looking at radius 1.5. Are we at the correct point of that? The second point is right here, where my mouse cursor is pointing at. You guys repeat that? This time I'm just telling the answer right here. Third point, the angle is 135, but then we're looking at minus 2.5. That's the third point that popped out. And then the last point here, we're looking at minus 180, minus 3. That point right there, that last point just popped out right here. So we got those properties right here. Right? So these are some of the basic properties we already knew about the polar coordinates here, and some relationship between polar coordinates and Cartesian coordinates. So from what we've learned here, let's look at example 2 right here. Where we get convert 30 degrees. Yeah. Okay. So that point right here, we plotted that in the polar coordinates, right? So it was already plotted. So now we want to convert this to Cartesian coordinates. So keep in mind that these are not x and y. These are not x and y. See what I'm saying? No? So the way how I'm seeing that now, the point is at 30 degrees angle. We've got angle 30 degrees. Okay? And we've got some radius being 3. So that's the point here. That our point is good. It's 3, 30. That's why we're writing it like that. But now, what are the x and y coordinates? The x coordinate is here, this distance. And the y coordinate is vertical distance. So right now I'm seeing the x coordinate is simply just, and we've learned from our trigonometry understanding that x value, once you have angle and you're going to know the radius, then we are in a circle that's other than the unit circle, remember? So the x coordinates can be just simply what the radius times the cosine of our angle. So in this case, radius is 3 times cosine of the 30 degrees angle. Right? So our x values here will come out being 3 times 30 degrees angle. Cosine of that is what, 3 over 2. See what I mean? So the x values comes out 3 square root of 3 over 2. That's the x value. We're getting ourselves ready for Cartesian coordinates. And so same way with the same exact picture, right? Y value we've learned from our previous learning in trigonometry. Okay? And you guys can review that at any time with that. But we're doing here r times sine of theta. So in this case, we get a y value is 3 for radius given. Right? And it's sine of 30 degrees. Okay? And that gives me 3 times sine of 30 degrees is a 1/2, right? That gives me a 3 over 2. So our final Cartesian coordinates for 3, 30. Now we're looking at 3 square root of 3 over 2 for x, right? And 3/2 for y. That's our Cartesian coordinates at the same point. What about negative 1.5, right, and negative 60. So the angle, the point itself, negative 60 goes about, we plotted it goes about negative 60 is like this, right? But instead of staying here, we go to the opposite side, see what I'm saying? Okay, so about the radius 1.5. So this point was the one that we have chosen like that. Sounds good? So, what coordinates, what x and y coordinates is that? So we're still going to follow the same rule. What we've learned now is x equals r times cosine theta. The only thing slightly different is r is given as a negative angle, negative radius. So negative 1.5, we multiply that with cosine of negative 60. Cosine of negative 60. Are we good with that still? So negative cosine of negative 60 turns out being what? So negative 1.5 is the radius, stays the same, nothing can be changed. Cosine of negative 60 gives me a 1/2, right? Now we're looking at altogether here minus 1.5 over 2, or so in decimals it's negative 0.75, right? or you can see that as negative 3/4. That's how we found the x value. And the y value can go, again, r equals sine theta. Here we can y equals minus 1.5 for radius times sine of negative 60 angle. Right? So negative 1.5 times negative square root 3/2. So negative angle is negative sine value, so now it's going to make it all positive. So positive 3 square root 3 over 4. So our final Cartesian point, Cartesian coordinates, negative 3/4, comma 3 square root 3 over 4. For example 2, we drew out also some other important information right here. That's the x value, also radius times the cosine of the angle theta. And the y value is also radius times the sine of theta. And these two relationships are specifically good when you're calculating from the given polar coordinates, right, and converting it to the Cartesian coordinates. So in our example 2, we learned how we can convert a point given in a point written in polar coordinates into Cartesian coordinates, right? So now we're going to learn to do the other way around. Those four plotted points. So let's find them one by one. These plotted points, they come with the label A, B, C, and D, right? And you can now notice that they are being placed throughout the 4 different quadrants of our axes, right? Of our graphing space. Okay? The whole, the origin is right here at 0, 0, needless to say. Right? So in our language at this point right here, we see the origin as a whole, right? So, point A. You see, in Cartesian coordinates, that's currently how these points are being written. Then point A is at 4, 3. This is x, that's y. Right? And so in that way right here, how much radius is it making with the pole? That's the radius amount, right? See what I'm saying? No? So now we can just recall for ourselves. From what we wrote down earlier in our lecture over here, the radius from any point, right? The distance to the pole right here is called the radius. That radius can always be calculated as the square root of x squared plus y squared. See what I'm saying? That? Okay. So in that way, I'm going to go ahead and calculate r here to be square root of 4 squared plus 3 r squared. All of that sum is inside the square root. Okay. Okay, so that means r here comes out being square root of 16 plus 9, that's giving me a 25. Right? Square root of 25 gives me a 5 again. My r 5. So that point makes radius 5, okay, from where my point is, from the origin. Okay. Now, before I go on a little too far over here, let me go back to the step. Let me go back to the instruction of the problem here. We want to. There are so many ways of writing the angles, right? So we want to just stay with the tradition that stated with the. For this problem here, we want to stay with the instruction that we want theta to be a positive, expressed as a positive angle, right? An angle in positive rotation. See what I mean? Okay. So putting that extra note for our problem again. Right. So now back to the work, we're in the middle of, and we're on our way there, right? We try to get. So we'll count the radius for our point A here. So now to calculate theta. Now theta, you can go with sine inverse, because now you got r, right? And your x is 4, your y is 3, right? You have your choice of going with these are the formulas I have on the board for you. You have the choice of using sine inverse, or cosine inverse, or tangent inverse. So, however, with the 3 little formulas right here, in my experience, I recommend using that one. I highly recommend that. With my highest recommendation right there, go with the tangent inverse. Because the tangent inverse is actually a little bit independent with your work calculating radius. You don't need to calculate it. You calculate the radius before you can calculate the angle. See what I'm saying? Huh? So with that recommendation, I'm going to head out with tangent inverse. And any inverse trig function has a little limitation, so you gotta watch out for that. So now tangent inverse, we're gonna fire up tangent inverse of y over x, so 3 over 4. Are we good with that then? Right? And this is the part where, see, we've learned previously how we can operate with tangent inverse, right? Especially we already learned that skill on the calculator. So you guys feel free to use your calculator. Now I want the final angle right here in degrees again. Right? Let's keep it all in degrees again. Okay? Degrees. Keep it simple for us. Okay? So keep your calculator in degrees. And then we want that to be expressed as a positive angle. (36.87 degrees). Okay. And so now we've got to carefully check with here before I put that in a final box, right? Does it look to be consistent here? The angle is a positive angle, right? As a positive rotation, so it does look about 36 something degrees here. See what I'm saying? Of course, my drawing is upscale right here, but it's surely in quadrant 1. The point itself is in quadrant 1, right? And so that information, the physical drawing of the picture that we had and the angle we found is consistent. So this is all good, right? So that point A right here. So now the polar coordinates of that, right? Final polar coordinates of this point right here, we're going to have the point A, same point, but we're going to re-express it as radius 5, right, and angle, and making angle 36.87 degrees. That's how we're doing this. Okay? I'm going to clear up the board, and we're going to move out to the next point. And really, these points that we're doing here, these points that we're trying to get the polar coordinates out of those, we don't have to do them in sequence, I mean in order, so whichever point that you want to be next. But it's just me, when I'm leading the example, I tend to go counterclockwise, right, around the unit circle, around the plane in the order of the quadrants. So how about, let's look at point B right here. The point B right now in Cartesian coefficient, right, in Cartesian rectangular coordinates, we're looking at -3, 6. That's Cartesian coordinates again. So again, that's x, right? That's y. So radius is easy. Always that's one fixed formula. Okay? So be sure to use your parentheses for negative. And that's why I highly recommend, anytime you're substituting in a value, right, for a formula, make sure to use parentheses. So -3 all squared plus 6 all squared. The sum of those inside the square root. So I'm looking now at square root of what? 9 plus 36, right? Which is a 45 again. Well, you can write this as a 3 square root of 5. That's after reducing the root. These skills in reducing roots here are some skills that you should have learned in the course prior to this, right? So be ready to use those. Okay? In case you need extra review, there are tons of video lessons on YouTube or Google that you can review your skills in those. Now, that's right here. Okay? So now let's calculate the angle. So theta here, once again, we run tangent inverse. Okay? The x and y over x. So y is 6, okay? X is -3. Sound good? Okay. Go ahead and run your tangent inverse to calculate the angle. Once again, keep your angles in degrees. we write it down, but hey, wait a minute. Does this answer look consistent? The number one thing we want positive angle, right? That's the instruction, and our angle is in quadrant 2. That's why I was about to do this earlier, but I decided not to until now. So the angle is indeed as a positive angle. It's like that. See what I'm saying now? It's just, there's nothing wrong with your calculation, but remember, tangent as by default, tangent is only giving out an angle anywhere from minus 502 to 502, okay? Or from minus 90 degrees to 90 degrees, okay, between that. So that's completely consistent with the way how you calculate it, right? But it's a little bit different with what we're expecting here, right? The angle that came out right here is about right there. This is about negative 63.43. See what I mean? So how do we go from here to that exact spot? So what's the trick then? What do you see? Look right in the picture. I mean, the other side right here that I drew down from the x-axis here, right? The other side I drew down is really just the opposite side of that solid line right there, right? Making a straight angle. So how big is straight angle? 180. So to get to the actual angle there, what do? We just simply add a 180 degrees. See what I mean? Right. So we do that trick simply because the tangent gave us this, and then we saw that it's a little bit inconsistent with the picture, so we've got to do that to 180. It's not always a fixed rule like that, but because we see that from the picture right there. See what I mean? So make sure you guys follow that explanation of mine carefully. So after adding 180 right here, what's our final answer right here as a positive angle? 16.57. Right. So we've got that one now. So now let's move on to another one. Right? So we've got to know where the picture of where the point is. So sometimes, like I said, in the worst case, sometimes the problem is just give you the point without drawing it, right? Without plotting it. So when you do the calculation, it's best to make a plot here. Okay. So that point C, right now in Cartesian coordinates, -4, -2. So that's x, that's y. Okay. Radius comes out easily -4 all squared plus -2 all squared. Okay. So that's mathematics. Square root of 20, which is a 2. Okay. -4 all squared is 16, -2 all squared is 4, right? Adding together is 20. That's these down there. Right? So we're going to now run and calculate the angle. We're going to run tangent inverse again. Tangent inverse. Y over x. So y in this case is -2, or -2 over x is -4. Okay. And that usually, go ahead and get that calculated for. Yeah, so I'm going to hold it right there a little bit. See, 26.57 is only somewhere in the first quadrant. You guys see it there? And the real picture, the actual picture of our point is down here in the third quadrant, right? 26.57 something. Right? Here. So we want that point down here, so we have to go a 180 degrees there. So that's similar argument again. So we've got to adjust, right, depending on how our picture looks again. Right? So I'm going to add 180. I agree. So go ahead and add it up. The final angle should be 206.57 degrees. Right? Now that means our final polar coordinates for this point, same point, right? Polar coordinates. That's the point at radius 2, square root 5, and then we've got angle 206.57. Right? I mean, that was a rule, but that means more things for you to remember. So I just want to all break it down to one rule and make sure you draw your point in there, right? To know what quadrant it is, and then we make the appropriate adjustment. You know what I'm saying? Otherwise, don't tighten yourself down too much into a rule, because otherwise that's going to be a lot to remember, right? Because there are too many different cases. All right. So now let's get on to the last one in our picture, quadrant 4 here. So that point D right now, 3, negative 3, right? Yes, this is X, this is Y. And so we're looking at that here as radius, calculated as 3 squared plus negative 3 all squared. Right? That's going to get 9 plus 9 is 18. That gives me 3 square root 2 after reducing the square root. Yeah. Now we're going to go theta can be calculated by firing up our tangent inverse. We're looking at minus 3 over 3. So go ahead and get me that angle. Negative 45 degrees. The number is pretty nice, right? Negative 45 degrees. And it looks almost agreeing with our work here, because quadrant 4, negative 45 is down here, see what I'm saying? No? So we thought we'd done, but actually, according to the instruction here, then this is not an acceptable answer, right? I mean, there's nothing wrong with the calculation, see what I'm saying? No? But we need the angle in positive rotation from the x-axis. So how big is the angle if we rotate from the x-axis to that angle in the positive direction? See what I mean? So in that way, the trick for that, to get there, right, we're actually going to add one complete rotation, which is giving me a 360 degrees added on top of the minus 45. See what I'm saying now? And that will land you into the exact, see, the angles will be coterminal, right? We've learned all those terms at this point here. The final angle over here will still be coterminal, so it's the exact same spot. We have to address that according to the instruction right here. Right? We want positive angle. So now go ahead and write it down like that. Calculate it out. So it should be 315, right? Positive 315. Right, so that means our final polar coordinates for this particular point here. It's the same point. It's just we express that in the polar coordinates. So radius 3 square root 2 with angle 315 degrees. That's how we're putting it. All right, so now throughout our times here, so most of the time we do it, and at this point, and I still want to keep this board here with all of the fundamental information. We got the radius, right? It has a general formula, and we already seen it, right? And then we can calculate the angle theta by firing up any one of these, but I would say these are a little more challenging. So I recommend, in my experience, I highly recommend using the tangent, the formula. And then we got these relationship right here as well, relating between the polar coordinates and rectangular coordinates, or the Cartesian coordinates. So now, let me point out for you guys. So polar coordinates gives rise to the idea of polar equations. So polar coordinates is one big topic, because it's one style of the way how we represent points, right? So after we've learned how to convert between polar coordinates and Cartesian, and then from Cartesian going back to polar coordinates, the next thing we're looking at now is just think about any point, right? You got a point, right? X and Y. So we used to know that X and Y has some relationship, because think about it, it may belong, the point here may belong to some kind of curve, right? And so the graph of the curve here, so that means when this point belongs to a graph right here, then X and Y has to satisfy some kind of equation, you know what I'm saying? No? Right? So the graph that comes out right here is an equation, right? equation in terms of x and y, or when I'm saying in terms of x and y, I mean an equation that's relating x and y. For example, you have seen this all over. Have you seen this parabolic shape again? Right? So let's just say the simple one, y equals x squared. It's an equation. See what I'm saying? It's an equality relating the two variables x and y, but these variables now, as we're having a deeper look at that, right? Every point here are expressed, and any one of the point here is expressed as in rectangular coordinates. And that's why the equation here shows the relationship between the two variables x and y. That's it, right? So now think about the same curve. It could be the same curve, the exact same curve there. But now think about what if all of these points here expressed as some angle, some radius with some angle r. Any point there make some radius theta, right? And then make some angle theta with the positive x-axis and radius r. So in the end, my point here is that the equation can be expressed, right, in terms of r and theta. See what I mean? Because in the end, r and theta are two variables as well, right? As you change theta, you come to different points, right? You change the r and theta, you come to a different point. See what I'm saying? So the equation like this, we call that it's a Cartesian, right? Cartesian equation, or just the traditional rectangular coordinates equation. But then for the same graph, for the same curve, if you really express the curve here, the equation as an equation that involves the two polar variables here, right? And so we're about to find out that the equation can be expressed in terms of r and theta. We call that the polar equation. See what I mean? Right? It's the same equation again, but it just we turning that into the expression that's involving the r and the theta variables again. Right? So that's the idea. That's briefly the idea. Before we get into some actual example here, I just want to mention to you guys a couple of other things here. Eventually we're gonna most commonly, right? Most commonly, we want to express r, the variable r here, the radius, as a variable that depends on theta as a function of theta. See what I'm saying? Right? So most commonly, the equation, that equation here expressing r, the variable r, as a function of the theta variable. You guys learned from pre-calculus 1 that what it means by being a function, right? So the right-hand side right here on this equation is only in terms of the theta variable, and then everything that comes out, the outputs, we call it the r variable. Yeah. Okay. But it's, in the end, it's still a polar equation. It's just the most commonly used form of it. It's just most commonly used. It doesn't always have to be in the functional format like that. Right? But most of the time, it's like that. Right? So before we even get into any kind of formal examples where I show the steps, let me introduce the idea. You see, an equation could be like this: r equals 5. Right? It's a polar equation. This one right here is a polar equation. What does that mean? This polar equation here, you can see that there's no theta involved, right? That's one thing you can see, no theta involved. So here's how you see it. The graph for this equation, it's best that I bring it on the graph here. So I'm going to just put in the decimals in here, you just type in r equals 5. Yeah. See what kind of a picture it gives you right there? You see the shape that it has given you? What shape is that? It's just a nice round circle, right? A nice round circle right there. What's r? So why is it a nice round circle? How big is this circle by the way? Radius what? 2, 4, and 5, right? So why is that the circle like that? Because the equation says r equals 5. That means radius constantly equals 5, right? No matter. So think about it. The situation is angle can change. Angle can change. We say angle at some whatever arbitrary angle, like radius 5. You change to different angles, and when you draw your equation, when you make the graph of your equation right here, we always the rule here is we go from angle from small to large, meaning and going in a positive rotation. See what I mean? Okay. So at some angle you at radius 5, some other angle you still at radius 5. Okay? At some other angle you still at radius 5. So in the end, the equation of all these points, right, r and theta, makes up a nice circle, radius 5. See what I mean? That means independent with theta, we always gonna have radius being 5. That's why it's a nice round circle. Okay, so that's the graphic there. So rule of thumb, start putting that in your notes. At some point from now on, from this point on right here, anytime you have r equals a fixed positive value, right? K here is a positive. See what I mean? You're talking about the graph, the polar, right? For this polar equation, your graph will be just that's nice round circle, right? The radius amount here is K. See what I'm saying? That will always give you the graph in a nice round circle and center right at the pole, right out at the origin, the pole of our graph. And that's why we're having that on our picture right here. Right? So let me zoom out a little bit so that you have a better view of that. Alright, so but now seeing the graph is only one thing. That's not the ultimate goal. I'm going to roll back after you took notes about the graph of this particular equation, particular family of equation. We got a polar equation. Now think about it. Don't we famously know that r equals the square root of x squared plus y squared? Right? We know that from our previous learning, right? And so from this case here, I had an equation starting in the beginning. My equation was written as a polar equation, but now I'm going to substitute. The 5 here is still there, but I'm going to substitute r by square root of x squared plus y squared. And the right hand side remains the same, equals 5. You guys with me now? So what I did here is I just simply substituted, right? Substituted r equals the square root of x squared plus y squared. Which r, and that's how I ended up with that. You know what I mean? But look at this final equation. Look at this final equation right here. It's still an equation, right? But now it's only relating x and y. See what I'm saying? Not only relating x and y, and the r and theta completely disappear. Right? It got completely gone right there. See what I'm saying? No? So this final equation, and another way of writing it, you can decide to square both sides, turning it into a cleaner form. X squared plus y squared equals 5. I mean, 5 squared, which is a 25. See what I mean? Right? Either one of these, if you take a close observation, only x and y variables involved, right? And the x and y variables are, what do we call the x and y variables? They are the rectangular coordinates, right? They are the Cartesian coordinates. And so now we're starting with a polar equation, but we've learned our way to turn that same equation, we turn that into a, what we end here, this is a Cartesian equation. Does that make sense? The equation in rectangular coordinates. That's what we did. Okay. So that gave rise to the idea that, hey, there are the kind of problems where you have a polar equation given, right? And we can make our way. The polar equation only involves the r and the theta as your variable. The theta may be missing. Okay? But being a polar equation, you only have r and theta involved. And then we can learn our way to turn that problem to turn that same equation into a what's so-called a Cartesian equation. See what I mean? Okay. By the goal here, the final goal here is only involving x and y, the rectangular coordinates, as your variables in the equation. See what I mean? Okay. So that's how we're doing it. Right? So now, that's just a general structure right there. I'm going to fire up an actual example. we're converting from a polar equation to a Cartesian equation. Right? You already had the goal that I was introducing in that demonstration earlier. So now let's really get some problem done here. So how about right here? Let's look at our equation here is r equals cosine theta. We've got to bring in a lot of algebra here. From what I'm seeing here, first of all, do you see that we can multiply both sides by, and there are many different ways how we can approach it. First thing is the polar equation, only two variables are in theta involved, right? So in how I'm observing it, I can multiply both sides by that variable r here. So I'm going to make it r squared on the left hand side, because we multiply r to both sides. R times cosine theta, the right hand side. You are doing that. Okay. So that's just one algebra step that I took here. But look at the usefulness of, and look at all that good thing that this algebra step has given us for you. Do you recognize r times cosine theta? The point again, see? X over r equals cosine theta. We know this from our trigonometry learning, right? And so this can also mean the same as if we multiply r to both sides, we're looking at x equals r times cosine theta. See what I'm saying there? And then since I'm on this board anyway, let me just further continue with this. See, y over r equals sine theta. We can also think of y variable equals to r times sine theta. You guys agree on that? Okay. And then this r equals square root of x squared plus y squared. You can also purposely square both sides, making it r squared equals x squared plus y squared. We have so many directions to make the correspondence algebraically. Okay. So now, what's good about that? So I was saying it a little earlier in the middle of it, but the point is to bring our equation to something that completely that only involves x and y variable, right? Only involves the x and the y variable. So you see that now you can replace, you can substitute this or cosine theta by what? By x. See what I'm saying? No? That algebra trick that I did earlier, I multiply r to both sides, I'm making it r squared equals r times cosine theta. Now I realize, wait a minute, r cosine theta can be substituted by x. Sounds good. What about the r squared? We can substitute that with what? X squared plus y squared, right? Now we have found our Cartesian equation. Because the point now is that we have come to some equation that only involves the x and y variable. So we have found our targets, right? We have reached our destination. Okay? So this is our final Cartesian equation. Getting some good hang of it so far?